Hello everyone. Today we're going to discuss hash tables further. I want to talk about an array-based hash table and a linked list-based hash table to show how these hash tables are one form of an associative array. There are other tricks we can use for associative arrays. And I'll describe associative arrays a little more in detail. The rest of the time, I got to move on to lab time. It was very definite over the weekend based on the panicked emails I received that yes, this needs more time. This assignment is very syntax heavy. I am leaning towards a similar syntax heavy assignment for the hash table assignment on Wednesday. Simply because, not because I want to be mean, but because you need to practice. The hardest part about this is that, as I've seen many times before, you get in a method, let's say like operator star or the linked list begin, and people have a really hard time keeping track of what's going on. What are my data members? What is this? How do I refer to the linked list data members or my iterator data members? Do I have linked list data members if I'm in an iterator method? And that it's hard because up to now, how do I say it? It's almost like if we did this in a school perspective. You think of everything in terms of first names. Hey, I've got this value data member and this info and this length, but you didn't really think there could be lots of links. And now what if you more and say it's more advanced where you have to say, we have a count belonging to the linked list. We have a current belonging to the iterator. And trying to keep track of data members within containers, it's just hard to do. And then you need practice. All right, so raise of hands who was done? One. Really? That's it?
I didn't know.
Hold on. I know other people are done. Who is, Brian is done. Who is not done? Raise of hands. Oh my goodness, we're gonna need a lot of lab time. So tell me, where are you stuck? And is it my fault?
Test 6.
Test 6 of what?
The first test.
The fundamental stuff. Fundamentals, just trying to get that down. Anybody stuck on our reverse? You wish you could get there? All right, so we're just gonna need a.
5 minutes ago.
Let's take a moment. If there's this many people stuck, a little conversation will help on it. So you're stuck at test number 6. What's happening on test number 6? Let me pull up that code here.
It's the postfix increment. So once you get down,
oh yeah.
you're
Hold on.
creating two things, iters and another iter.
I love how mean these assignments are. So no, that's linked list methods. I need
line 431 on mine, so it's probably
iterators. Open file. All right.
Yeah. So on your 325 and 326, so when I go into the debug mode, I see that iter I passed test 5.
Yes.
But when I go to test 6, it doesn't show 2. It shows that another iter is starting on 4.
Uh-huh.
And I can't seem to wrap
Okay.
my head around.
So here's what's going on. This is for many of you have never done postfix before, and so this is a fun reminder of what postfix is. Postfix is a hacky way of saying run the highlighted code first, then run the ++ afterward. So what occurs here is that we start by creating an iterator. That iterator is pointing to the 2. We have our numbers 2, 4, 6, 8, 10, and so on. This iter is pointing to the 2. We make a copy of the iter. Whenever you see this assignment on an object, almost always it's making a copy of it. So iter is making a copy of itself into another iter. So after that highlighted code makes the copy, both iterator objects are pointing to the 2. Good so far? That's what needs to happen.
Yes.
And then after that is done, the ++ effectively fires, and it moves that iter from 2 to 4. So when we're done, iter should be at 4. Another iterator should still be back at 2. They're not sharing. We have 2 iterators here. Everybody okay with that so far? All right. How do you solve this? In your operator ++ that has an int in the parameter, Do you have that?
Mhm.
That int in the parameter is a hacky way of saying this means postfix. You want to do the following steps in this order. Number 1, make a copy of this. You do that with something like auto temp equals star this. Then move the this iterator forward if possible. Can you move it forward? If so, actually move it forward. If you called your pointer current, then current is equal to current's, this current's equal to this current's forward, or whatever you did. If you can't, you have to set that off the right cliff to true. Then what do you return? Do you return a copy of this, or do you return a copy of, or do you return temp? You return the original temp.
So I return star this.
Yep, that's going to return, because what your code is doing is it's moving the object itself forward, and then now that it's moved forward, you're returning a copy of it having already been moved forward.
So I should have been returning like the current.
No, you return that original temp. See that temp up above? That temp is like saying, let's get an original state of what it is before it's been modified. Then let's modify this, and let's return the original temp.
That would make more sense. Because it kept starting on 4.
Right.
and I was-
No, you're fine. There's a lot of details here. By the way, this is why a prefix plus plus is often considered to be more efficient than postfix plus plus. When you're done, take a look at your 2 operator plus pluses. Which one has less code? The prefix. Does the prefix make a temporary copy? No. For that reason, as much as possible in your for loops, you should be doing prefix or getting in the habit of it. For ints, it doesn't matter. It's not really hurting anything. But for objects, yeah, it's got to make a copy, and that copy is inefficient. All right, so you said you were stuck on test 7,
Yeah.
but that's just saying it should display the following values, and it's not.
Yeah. So I display 2, 4. I pretty much display all of it without the period, and then it just kind of gives me the unhandled exception.
It's not displaying the period, you say?
Yeah.
It shouldn't display the period. That's just
Okay. Well, it just gets stopped there. Then it just gets stopped.
it gets stuck.
Yeah. It displays the entire list, and it just stops.
Wait. Does it hang or does a program crash? Does it get stuck in an infinite loop?
It throws the unhandled exception. So,
I'd have to look to see. We've got a few people saying it's not showing the 20. If it doesn't show the 20, likely what's happening is that your plus plus isn't going to the, how do I say it? We talked about this before, that we have to simulate being 1 past the end. Your operator plus pluses should be able to say if the forward's null pointer, I'm sorry, if the forward's if our current's forward is null pointer, should we actually go forward?
No.
No, but what should we do? Flip that boolean to true. Otherwise, we actually go forward. Does that make sense? That's the first half. The second half is making sure your operator not equals works correctly. The operator not equals needs 2 parts. It needs to compare. Did I put it? How much did I give you of this? Nope, good. You should have one parameter for your operator not equals. I call mine RHS for right hand side. The this becomes the left hand side. You compare the 2 iterators, and you have to compare both their current addresses, or whatever you call their pointer. Compare the addresses. Also compare their booleans off the right edge. If you don't compare both things, both sets, it won't work correctly. Some of you have been comparing infos. You're comparing your pointer's info with the other pointer's info. That's wrong. You're not comparing values, you're comparing pointers. Does that help you, Jessica? Now, I don't know where your bug is. I'm sure it's something simple. The best thing to do is step in, step out very carefully as it gets close to it, and you can see exactly what your logic is doing. I can't emphasize debugging enough in this class. I don't know how any student, in fact, I don't know if I've ever seen a student get through this class without using the debugger. If you think, oh, I'm smart enough, I can avoid it, no, it's life is better. Put a breakpoint here, step in, step out as needed. All right, where else are people stuck? Because I know a lot of you are going to work on your assignment instead of listen to me. like to give you some help. Nobody else wants to say anything?
Maybe that's where we all.
I was having a little bit of trouble with my decrement.
The decrement?
Yeah.
So the decrement's a lot easier. You don't have to. There's no such off the left cliff. Decrement's a straight. It could be a one-liner. No, it should be a two-liner.
Yeah.
You need to set. You always need to flip the Boolean to false. Because you could be off the right. There's two options. You could be off the right cliff. If so, if you move back to the left, that Boolean is no longer true. You're not on the right cliff anymore. You're now back on the list. So you have to flip the Boolean back to true.
No matter
I mean, you flip it back to false. Sorry.
false, yeah. We're not off the right cliff.
Correct. And if you weren't off the cliff, just still flip it to false, or leave it at false anyways. Just set it to false because it will go from false to false. Who cares? You don't have to do an if check. Just reset it to false. It's simple.
Okay.
There is no off the left cliff. So just move it to the left. Move it backward. And I never throw a test at you to try to make it crash, because that's not behavior you should ever have to deal with.
Okay. Thank you.
Other questions? Yes.
I just want to make sure I understand the off-right cliff. So if you're doing the plus plus, and how did you word it? The currents forward.
If your your iterator object should have a pointer to a node in it, right? Most people are calling theirs current. If your iterator's current, if your this is current's forward link is null pointer, then should you actually move your current forward? No. So what do you do instead? Flip that Boolean to true.
What do you return?
For operator plus plus, what you would have returned anyways. Return star this for your prefix, or return that temp for your postfix. That doesn't change.
Which is of type iterator.
What was that?
The not equals is looking for that right hand. Is supposed to look for that off the right.
Yeah, you have to compare, because it's very possible that the off the right cliff is simulating being one node past the edge, but there really isn't one extra node. So both iterators could be pointing to the same last node, but their Booleans could be different. One could say I'm really on the last node, and one could say I'm past the last node. And now they're really in technically different spots. Does that help? By the way, I have seen one student actually get frustrated and try to create an additional node, and it didn't work. It broke tests later. You cannot create a dummy node on the end. It doesn't work. I love how many students are freely in this class. Oh, I'm the person who did this. First day of the semester. Some people haven't passed this class in the last semester. Several students. That was me. I'm 4 times in. You guys crack me up.
So on that operator not equals, where we're checking to make sure that both things are pointing to the same place, and we're checking the Boolean value
Yes.
as well.
Yes.
How is it that we're
If they're all the same, you return false.
okay? I'm just not understanding the syntax as far as how do you check RHS's Boolean value and then also your current or whatever.
Very easy. So your left-hand side is your this. So if you might, let's say we're going to check the Boolean values. If this arrow off the right cliff equals RHS dot off the right cliff. Does that make sense? They're data members. You have two objects, and they both have data members inside them.
Yeah.
So you just have to you just have to say which one is it.
And I get confused as far as which one do we use the arrow for?
Okay, anytime your thing is a pointer, you have to use arrow. If it's not a pointer, you use a dot.
This is an object.
Was there other hands? Just yawning. All right, other questions? Free help. You pay good money to be here. It's what, like 20? Was it $10 or $20 a class period you pay to be here?
$23.
Was it 23? Was it really? That's right, it did. Ugh.
How do you remember that?
I remember that every time.
Speaking of which, let's take a quick game update. Ooh, they're still ahead. That's high scoring. All right, let's keep going.
Just keep the game on.
I'm getting nothing out of this, even though they're there.
Is it debug it? Walk through it carefully, step by step.
I'll say I just did, and every time it like goes, data's 2 now.
No, step through, watch user debugger carefully. That's all I can tell you. It's got, I don't know what it is right now, but your debugger will find it.
So if you set the off the right position, what's supposed to happen?
Oh, okay.
Well, that just simulates being one past the last node. Your not operator not equals needs to help enforce that by also checking for it. I mean, it's just a Boolean. It doesn't do anything special. It's how you use the Boolean that matters. Brian says, a pointer that points to a node on the heap is also a pointer on the heap, and you can compare a pointer on the heap to a pointer on the stack. Yeah, I mean, they're just addresses.
So if it's in that, that would mean that if it's in that for
Well, Jessica, you can't say this equals current because the data type of this is a pointer to your object. Well, current might be a pointer to, say, your node.
that kind of for loop work.
And the two aren't going to be the same kind of pointers.
If there would be
So if this is a pointer to an iterator, I think you meant to say something like this current is equal to right-hand side current. Is that what you're getting at?
But that's why it's throwing the errors, because you're saying something different. 'Cause it's not
Now they're currents, both currents are node type pointers, so now you can compare those pointers.
defined that here, because you don't have a return key.
You have to be careful. You can't think they're just addresses because they have to be addresses to something. This is an address to an iterator. Current is an address to a node. Very different kinds of addresses. All right, more questions? Or should we move on?
In the, we talked about the not equals, but does the,
All right, say your question again.
so with the not equals, we compare the Boolean plus the location or the pointer locations to make sure both of them are the same. We would do the same 2 checks for the
Yeah, the equals equals the exact same checks, except instead of returning false, you would be returning true.
well, any for loop that's a range.
Other questions? Yes.
So how would you compare the pointers for the if statement? The next.
It's the only reason.
How do you compare the pointers for the if statement in like your operator not equals?
Yeah, would it be like RHS?
You mean like this kind of text that I have in the bottom right-hand corner? It's hard for you to see. Maybe I should make it a little larger.
Now, do we need to make an operators equals equals?
You do because the STL algorithm's reverse method, it insists on having an equals equals.
Okay.
It's frustrating because they could have just negated the not equals because the not equals is more common in the iterator world. But yeah, to use the reverse method from theirs, it has to support an overloaded equals equals. All right, in the back though, does this answer your question for you?
So you can almost put the exact same code in the not equals and just change the comparison.
Hold on. Somebody muted me. You guys, can you hear me? Is my recording still going? All right. That was strange.
So the operator is not equal to operator equals.
Say that one more time.
The operator is not equal to operator equals. Aren't they almost exactly the same code?
Yep, it's almost the exact same code. In fact, some people will just have one call the other.
Yeah, that's what I did.
So you can say it's your call. Whatever you want. It's simple. Don't overdo it. It's a one-liner. Either way.
Because Boolean.
All right, Jessica, you happy now? Do you have enough? You got the audio, you got the video. What else do you need? Jeez. Here, since you asked, we'll do a. Let's see what Lolcats has for us here. Some of the original ones. What's a good funny one? Oh, one of the originals. I must go, my planet needs me. I Has a Sad is a classic. Invisible Bike. It's one of the originals. It's been cropped out. You guys don't know about LOL cats? Remind me when things get kind of dry, and we'll talk about the LOL programming code.
Okay.
Is that like the has?
Yeah, we'll get to, you know about it. We'll do it. All right, let's get back here. All these online students are wondering what's going on here.
I just tried to find out if
Whoops. That's what was... I was smelling a burning smell. I put my AC adapter right next to my out vent and... like, what is that? The laptop was overheating. All right. So let's move on with hash tables, hash functions. Let's pull this up here. We will start with our friendly array-based hash table approach again, just as a review. And then we will move back into an a fully array-based hash table and quickly describe these. All right, so again, what is the main purpose of a hash table? Why do we like them? What's so nice about them?
They're a quick way to verify information.
That's a very open-ended answer.
If you have, like, I just think of password, you can put a password in, but instead of keeping the password, I keep your hash table.
Okay, that's not a hash table, that's just a hash function.
Hash function, okay,
So,
Yes,
It provides good distribution due to the algorithms.
so a hash table should have good distribution. That's one feature of it. What else?
should hopefully speed up search times.
Good distribution, fast search times, fast search and insert. What else? These are very vague answers. By the way, if you say these kind of vague answers on an exam, you won't get points. I'm sorry. Random doesn't tell me anything. What else? The biggest thing about a hash table is that it's meant to work in a key value pair system. In other words, if somehow you can supply a key, using that key we can hash it, do some work on it, and then be able to store the entire value, the full object, into the hash table. Anything that's a key value pair is generalized into an associative array. A hash table is one kind of associative array. There are other kinds of associative arrays. The idea of associative array is that it's a key value pair system. We'll show you more examples of that in just a minute. All right, so suppose we had let's do some, tell me in start to finish, the process. If we have a key, what do you do to the key? You look it up how? Doing what? What did you say?
What?
It was somebody else. Look behind you.
Use your key to look up the value.
How do you use the key to look up the value? There's a process we go through. This is a really important process.
You,
You put it through an algorithm.
you look at for example.
Okay, so we hash, not that you don't hash the value. That's wrong. You hash what?
Hash the,
Hash the key.
Hash the key.
And compare the
And then what do you do with that hashed value?
You take however much of it you want.
Take however much of the hashed key that you want, and use that to look up a bucket. We didn't talk about this much last time, but a very common trick that people do to say take however many we want is you mod it. We were saying let's maybe take off that last hexadecimal character, and now we have 16 buckets. Or we take off the last two, and now we have 256 buckets. What if I want 13 buckets?
Just mod 13.
The nice part is you simply mod, I will say mod by the number of buckets.
Well, no.
So if you take some big integer output and you mod by, say, 13, what will you always get? Some value between 0 and 12. And will it still be well distributed? Yes, because your hash function was well distributed. For those of you who've forgotten what mod is divide but give me the remainder. So what is 13 mod 5? 13 mod 5? 13 divided by 5 is normally 2, but with a remainder of 3. So we're not worrying about the division part, we're worrying about the remainder part. So yes, 13 mod 5 is 3. Everyone okay with that? What do you do with that number that it gives you? After you mod it, what do we do? You go to that bucket, that container, whatever you want to call it. I like thinking in terms of buckets. Go to that bucket, then what?
Search through that bucket.
Depending on if you're doing an inserting or searching, search down that bucket for a matching key.
Now, is it the original key or is it the hash of the key?
No, the original key. And then once you find some object that has the matching key, then you can say, aha, this piece of data has the matching key. I restrict my hash table to have unique keys. That's why we have unique W numbers or social security numbers. And then from there, I would say this data object must have the value I'm looking for, and it returns the object. Yes?
Do you create the buckets beforehand?
Yes, you need to create all the buckets beforehand.
Is there a special way to do that?
That's what we're going to talk about. There's linked list ways and or array ways. So we're going to start with an array of linked lists. Perhaps the cleanest way in terms of using tools, and it allows for easy growing of your data. So let's start. I will create an array. Let's make this hash table rather small. We will put 8 items in our hash table, or 8 possible linked lists. So I have an array of linked lists, and I will make a key on these. This is my array. Let's do another color for linked lists. So each one of these will have a linked list object inside of it. Does it scare you to have 8 linked lists floating about? Could I easily have 1,000,000 linked lists floating about?
Would it actually have a link list inside or just a pointer to the link?
It would have it depends on how you set it up. Most of the time it's a linked list inside. But all linked lists are basically just first, last, and counts. And I'm just going to draw the first and last for right now. Sound fair? All right. And let's go through and get some values. I'm going to start, I've picked on the front too much. Let's start in the very, very back. I need some names. I know Doug. Doug, if I were to hash your name and then mod it by 8, what number do I get between 0 and 7? Okay. Tell me a number between 0 and 7. 4. So Doug hashes to 4. So what that would mean is I would go to index 1, 2, 3, 4, and I would create a node. And in this node, I will put in your situation, let's say the key is your name. It's not a very good key because we can easily have duplicates, but for now, this gets the job done. So I will put in here an extra data member for Doug, and I need some kind of object to represent Doug. How about Doug, what's your favorite number? Or do you have a favorite number? 7. So this is the important information I have about Doug. Better yet, how much money do you have in your wallet, but you can lie if you don't want to give away anything important? 0. All right, so Doug is worth 0. Sound fair? Don't worry, you're the last, but the last will become the first. And the first will be the last. All right, so we've got Doug in there. We're pointing here. I won't worry about updating my last pointers. I think you get the idea. Can you tell that this green thing is a node? I've got the key inside of here, and I've also got the data object inside of here as well. Is that all right with you guys? All right, let's keep going. On the back, name.
Carson.
Carson. If we were to hash your name and mod it by 8, what will we get? Is it ON?
Oh, yeah.
Carson, what do you hash to?
I don't know,
7. All right. Carson, how much money do you have in your wallet?
like $5.
Okay. That's what he wants us to think. So I will put a Carson is my key, and then I need to make sure that I have $5, and I'll have my link on here. And I need to make sure I draw these. These are nodes. You know what nodes are. And I will do, these will be student objects. I'm trying to draw different data types in different colors. Just so you know, there's a lot of data types involved here. This is a heavily tools-based data structure. All right, let's keep going. In the back, I need a name. Daniel, how much money do you have in your wallet? $4. All right, you also have 4. Oh, I'm sorry, no, I don't need that. What do you hash to between 0 and 7? 0. But you have $4. So we'll make a node and insert you. So let's see if I can get Daniel here. Cram that on in. There's my link. And you have 4. All right, let's keep going along the back. Name. Joshua. If we hash your name, what do you hash to? 5. How much money do you have in your wallet, Josh?
I roll in $20.
That's who we jumped.
All right. All right, let's keep going. Up here. Dylan. What do you hash to?
Can I go 4?
You can also do 4. Thank you for doing that.
Yeah.
So I have another key, another key hashing to 4. If you ever have 2 keys hashed to the same location, it is called a collision. Is a collision necessarily a bad thing? No, in this case it's not. I mean, we're going to expect them eventually. All that matters is that we say, all right, on the 4th linked list, let's just do another insert last. So we simply create another node. And I will put the Dylan key here. And Dylan, how much money do you have?
I would say no because I'm not carrying a wallet. I guess I could
No
also
wallet
say-
at all?
I'm carrying.
What is the cash value of all your clothes if you were desperate and you went to a pawn shop?
Oh, $50.
Really? Your clothes are worth that much?
Well, your shoes are worth like.
Oh, the shoes are, all right.
And my jeans are worth like 20. So.
All right. Now, what if somebody else hashed to 4? What would we do? Append them onto the end. Does that make sense? Do we need to keep going, or do you get the idea? Is it possible we could get done and there might be 4 or 5 in bucket number 4, but still nothing in bucket 2?
Yes.
It's possible, but we would assume that as we add more data to this, if we have a good hash function, eventually it should become well distributed. Correct? Law of averages. So the beauty about a linked list based hash table is that can it grow easy?
Yes.
Can you remove items?
Yes.
Can linked lists remove items easily?
Yes.
Yes. Does it use compact size well?
No.
Why not?
Well, you're creating each. You have multiple linked lists inside your array, and whenever you create them, you create a node on them, and therefore, you like now right now. You
Yeah,
can
so
have-
what? It's not too compact size, of compact size, because all of our nodes need some extra 4 or 8 bytes for an extra pointer.
Yeah.
That extra pointer is extra. In one way, you can think of it as wasted space. Is it necessarily fast? What if I only had 8 buckets and then I put 20,000 students into this hash table?
No.
Why is it not fast?
Well, every time you have to search through nodes, searching, during the array is quick, you can go through an array. very
Yeah,
quickly.
if you had 20,000, you're having thousands. If you had 20,000 students in 8 buckets, then each bucket will have thousands of students in it,
Yes.
a few thousand. And if that's the case, how much work does it take for a linked list to go search a few thousand? It can take a while. I mean, it depends. You know, the more you hit it, the worse it looks. So is it speedy?
Yeah.
Speedy is the official term.
Depends on the size.
I heard
of your array.
I think that's a good description for it. Not really. It's not that. I would say no. It's not the best. It depends how you set it up. What if you have more buckets than you have data that you'll ever put into it?
Then it's a lot quicker.
Then it's a lot faster because how often will you be doing hop by hop down the linked list? Not very rarely, because you've got a lot of buckets just won't get used at all. A lot of them will just have 1 in it. Is that making sense for everybody?
Yeah.
I thought that was super slow though. As far as searching into the bucket, it's really fast, but to get to that particular bucket, isn't it really slow and inefficient?
No, to jump to an index. This is where the random access part of RAM comes into play. To say, I want to go to linked list number 4. How quick can it do that?
Really quick.
Very fast. That's what RAM does. Any address, go to it, bam, you get it, bring it back, you got it. It's there. That part's fast. Hopping pointer by pointer is the slow part. So the full process to look up data is hash the key, mod by number of buckets. How quick is that process? Very fast. It's very fast. How quick is it to go to that bucket? Very fast. How quick is it to search down that bucket for a matching key?
Okay.
Can be slow.
Okay, so let's just take this class right now.
Yes.
If we did a mod, let's say we did mod 40.
Okay.
So we have 40 buckets.
Mm-hmm.
And therefore that's much more than we have per people in the classroom.
Yeah, let's say we have 25 in here and we mod by 40.
So we would have multiple lists there. When we search, it can be we're more likely, if we had 2 in one list, that would be very unlikely.
Right. I mean, but you'll have most buckets will have 1, some will have 2, a couple might have 3. Yeah, that'll be a nice speedy list or some nice speedy hash table. Does that?
Yeah.
Are we okay so far? How about this? Can a linked list do repeated removes and inserts?
Yes.
Yeah.
Repeated removal and inserts. In other words, is it good to reuse data well? Can you empty a list out and then fill it back up and empty a list out and fill it back up?
Yes.
Yeah, that doesn't really seem to hurt it. How about, can the hash table grow? Not a list, but can the hash table grow?
No.
No. Does that make sense? What if I start off with these 8 buckets and then I realize, whoa, I have 20,000 students now. How about I make the hash table grow? How do you do that? Yes.
You could make a copy of the whole thing and make a new hash table.
Mm-hmm.
Or, I don't know if this is a good idea, but what if you left like an empty space on the end, and if you reach the end, make a pointer to a new hash table.
So your second approach is to say, let's say you could have more room to grow if desired. The trouble with that is that your initial hash table will still have way too many values in their buckets. So you don't want to try to append more buckets midway. The first approach you said was better. Create a brand new hash table that's resized for a lot more buckets, and you basically have to re-index. You have to reprocess every value one by one.
Yeah.
How many of you have taken the database class? 2550. What does it mean to index a table? Why would you index a column of a database table? What does that do for you?
Speak up.
You guys know? Denise?
No, I took that class probably.
Do you know?
7 years ago.
You're like, I took it. It usually makes it faster. That's your hope. A lot of you are like, I don't know, it's slow. We'll try indexing it. Hey, it went faster. It's like some magic button. Why don't they just index all the time? Because there's overhead attached to it. The ideas that we're doing here is very similar to re-indexing a column of a database. Just say, hey, it's kind of... a column of a database that hasn't been indexed is like a flat array. Like the aisle at the supermarket that's 2 miles long. How long does it take to find an item? A long time. Indexing a table of a database, often they'll use a hash table to index tables or index columns. So now that column might be a lot faster. If you ever need to re-index it, you could re-index it. Indexing initially takes a long time, but it makes your lookups much, much faster later. Are we okay on this so far? All right. We are going to move to a system where we no longer have linked lists. I want to do a fully array-based hash table. So I'm going to get rid of all these. Let's get rid of.
Deleting what's hard to do.
I think it makes a lot of things more obnoxious. Let's say you're working with some kind of an operating system that doesn't have a heap. Or if it does, you don't have access to it. You cannot use new or delete. You can't just make nodes on the fly. You have to know everything compile time. So let's say that this is my whole hash table. I have 8 buckets, so I can only fit at most 8 students into it. We're going to go back, starting with Doug. Doug, you get to be created here. And you had, what, $0?
Yeah.
And there's another problem we have right off the bat. Arrays aren't really meant to store 2 different kinds of data. Arrays, they're homogeneous. They should only store 1 kind of data. So I am going to make a second array here to hold the key. And this will hold Doug, the key. So if this guy is the key array, then the top one is the value array. Is everybody okay with this so far? I have 2 arrays storing my data. The arrays are always the same size. If I had 100 buckets, then both arrays would be or have 100 elements in it. But every time I insert, I'll store the key in one spot and the value in another spot. That lets me easily have arrays that are homogeneous data types. We okay so far? All right, let's keep going. Carson, where did you hash to? 7. Let's make sure I write a 7 in here so we know. All right, Carson, you get to go here. And how you had what, $5? Is that right? All right, Daniel. You also had $0. Okay, and we have Josh. You get to go to. Didn't you have 20, Josh? 20. All right. So now we are at Dylan. Dylan, what did you hash to? 4. We have a new problem. I would like to put Dylan into my array-based hash table. But Doug is there. Suggestions.
Put him into one of the
Open
other
access
open
slots.
So what?
Put him into one of the open slots.
Don't delete Doug, just put, should I put it here or here?
No, just put Dylan into 3 instead of 4.
You just stick Dylan right there.
Well, I would put Dylan in the next open available slot.
So would you go backwards or forwards?
Forwards.
You'd go forward. So you put Dylan here. Anybody else?
Make another array.
Make another array. So that way you can have spillover values. So you'd have a value array 1 and a value array 2 and a value array 3. So hopefully you have enough to cover it. That's more or less a 2-dimensional array.
Yeah.
We're not going to do 2D arrays. They blow up in size fast. Like let's say you have a 10,000 buckets. Now you're wanting a 10,000 by 10,000 array. You might get away with something smaller, but that's a lot of wasted space. So we will avoid a 2D array.
Is this not a 2D array though?
No, this is like a 1D array and a second 1D array. The 2D array approach is saying, let's say, it's going to be hard to draw. Give yourself enough spillover space per bucket. So if I wanted to put Doug here, then I could also put, I'd have to have copies of values and key. So if I did a, can't really draw this. They should have been separate arrays. This is a 0 for Doug. Then I could do Dylan, you $50 for you. These would have to be different data types, but you can keep having more spillover room. Does that make sense? The problem is a lot of buckets will go unused, or a lot of extra space will go unused, and that's a lot of wasted space. Way too much to be useful. So I'm going to ban this approach. No 2D arrays. Other approaches. What if you had an array that the first value was the hash? You got to describe that more. Well, he describes it. Other ideas. Yes, Dylan.
I don't have a heap, but do you have a pointer somewhere else on the stack?
You could. What's one approach that I have seen is people will make their own giant buffer. They say, hey, let's just make ourselves a big buffer of, say, a megabyte. And let's try to manually allocate our own nodes within that 1 megabyte buffer. So they fake a heap within their program. You could. We're not going to do it that way.
Like sections of numbers dedicated to a mod?
Well, what do I do with you, Dylan? In your give me an answer, not some half idea. Where would I put you?
So, do we have to use these same tables that we already have?
Or you want to add another table?
Well, what I was thinking was, what if you had like 3 array slots per mod, and then something that helped you figure out.
So you still like the idea of having triple room in here? Like, what if you just open this up to have 3 in here? Is that right? That's more or less just creating 3 arrays anyways. You're just trying to make it one-dimensional, but it's really two-dimensional. You're cheating. Other ideas? Just put him somewhere else. Seems to be the best option. Should we go to the left or to the right? Let's just go to the right. So if Doug stubbornly not moving from his spot, we will stick Dylan here. All right. Let's say I have this hash table and then I want to find Dylan. All right, Dylan, let's find out how much money you got. Let's see, I'll put into the system Dylan, we hash your name, we mod it by 8, and it comes up with 5. I go to spot, oh no, you hashed to 4. I go to 4. Are you there, Dylan?
No.
No. So does that mean you're not in my records? What does it mean?
Move down until we
I have to keep searching. So this means that in an array-based hash table, simply looking and finding a negative result doesn't mean we're done yet. What do we do now? Look here. All right? No, you weren't there. How about there? Yes, we found you. All right, we found you. I see your shoes are worth $50. I rob you for your shoes. All right, let's keep going. Denise, you're next in line. Denise, what would you hash to?
3.
Denise hashes to 3. Suppose I have not yet put Denise into the system. Is that how you spell it, Denise?
No.
No, tell me how to spell it.
D-E-N-I-C.
Like that?
D-nice.
Be nice. All right. So how would I look up Denise? Take her name, or key, hash it, mod by 8. I get a 3. And are you there? No, do I have to keep searching?
Question.
No.
Why?
Maybe.
That would mean that's the first one to go in. Right?
Because it's a blank spot.
Yeah.
If we find a blank, then we don't have to keep looking. Because, hey, we don't have to keep searching to the right. Yes?
Question. If this is a table that remove and add data, we will still have to look because.
Oh, we're going to get to that.
Okay.
Don't jump ahead. Thank you, though. Yeah, another. You're worrying about deleting and adding. Let's keep going. So we'll get back to you, Denise. We know that Denise is not there. Who wants to? Somebody else hash to 0. I'm sorry, I need the name. Name? Jimmy. Jimmy, you hash to 0. All right, if I try to look you up, what's going to happen?
Maybe somebody already did.
There's somebody already at 0, so then what do I do? Go to the next one. It's empty. What do I know about it? You're not in my hash table because I found an empty spot. All right, let's keep going. I need a name. Brandon? You hash to Brandon. What do you hash to? You hash to 4. All right, Brandon. I would start at 4. Are you in spot 4? No. Go to 5. Are you spot 5? No. Go to 6. Are you there? No. Go to 7. Are you there? What do I do here? Do I just say you're done? Remember the Q assignment? You wrap it around. Here's 0. Are you there? No. Here's 1. Are you there? Can we finally stop searching? Yes. All right. So one problem we begin to see with array-based hash tables, they clump. So do they clump when filling up? Yes. Do you know what I mean by clump? Various collisions start to... You're not just dealing with collisions on the same value, you're also dealing with collisions adjacent to each other. They all tend to pile up together. And that makes the lookup times much, much worse. All right. So, David, who dies? Who on my list had a terrible car accident? Doug. All right, actually, that's who I wanted to have die. for computational reasons.
Now, do we want to put the...
No, Doug dies. Doug, how did you die? Make it a heroic death or a sad death? What did you do? Heroic death. You saved a bunch of squirrels crossing on a highway. All right. So Doug is gone. So our first instinct is to just say, well, Doug is gone. Okay. Now, Dylan, I'd like to look you up again.
I'm not there. We don't have to keep searching.
Oh, hold on. So Dylan, you hash to what?
4.
4. Okay, I go to spot 4. What do I see?
Nothing.
Nothing there. It's empty. So I stop, right?
I don't exist.
You don't exist. Is that the behavior we wanted to see?
Yes.
Dylan doesn't want his shoes gone. So how do we fix this dilemma? Do you see the problem? Removing stuff creates these holes, and we don't have a solution for these holes yet.
Put a value in there like null.
You want to put some kind of value in here like null? You don't know all the...
Kept the key
What if you kept the key in there
and deleted
but deleted this? The problem is how do you really delete data? This is a problem you're going to see is there's no real code to say this object has now been deleted. You can't just say null pointer because they may not support null pointers. You can't just zero it out because that might not make sense. You can't, well, it might not be integer data type.
Oh, no?
It could be, instead of how much money do they have, it could just be, what's the name of their pet? That's not an integer.
Do we have to have like a special thing for every data type?
A special thing to, yeah, actually you're barking up the right tree. The solution to this dilemma is to create a third variable, or a third array.
Is it deleted?
It's a status. And the status, we can use number codes. We actually need 3 statuses. Nothing. Then we will have in use, and then we will also have deleted. So we'll initialize everything to 0 if it has never been used. If it has been used, let's put some 1s in here. This was not used. What about Doug who died? What should we put in his spot? -1 means deleted. You can make whatever code you want. If you want 2 to mean deleted, that's your call.
So even going through these 3 arrays, is that still faster than using the nodes within an array?
Yes, because these things are arrays. They fit well into cache.
Okay. Even though
Cache is ridiculously fast.
But if it was multi-dimensional, that might not be fast.
No, multidimensional won't fit into cache as well.
Okay.
This is Because the nice part about cache is if you look up Dylan, you're probably going to have Doug in your cache, and Carson will be in your cache, and Josh will be in your cache. So when you do subsequent lookups, the data will be in there. Arrays are fast. All right, so Doug, we killed off Doug. We put a -1 there. Now here's the trick: when you delete something, do you actually remove them? Is there an easy way to really delete an object? No. A common rule of deleting is you don't delete it; you just mark it as deleted. Standard operation in file systems, databases, data structures. There isn't really a thing of zeroing out bits. You just lose track of it, or you just say, "Don't come here." That's your deleting. So Doug is like the ghost of Doug. I wonder if you'd make a haunting ghost, Doug. Or what if there's such thing as a boring ghost? Yeah, my house is haunted. What does your ghost do? Nothing really. Just read the newspaper. And nothing else? No, it doesn't even look at me. Have you noticed that? It seems like all ghosts do something, and often it's scary. I've never heard of an average ghost story. Yeah, no, it was just the boring ghost. Or there's like ghost pets. What did that ghost dog do? Huh? I just stared out the window. What else? That's about it. All right. So now, Dylan, we want to look you back up. What do? You hash to 4.
So we're going to have to check our status code.
So I look at the status first. That's important. Do I look here at the key first? No, you look at the status first. -1, what does that tell me?
It's deleted.
So there was something there. So what do I do now? Look at the next spot. Status is a 1, so what do I do?
You gotta check.
Check the key. Does the key match? No, so I keep looking. Status, 1, check the key, matches, then grab the value back out. Make sense? Brandon, we're going to put you into the hash table. How much money do you have in your wallet? 0. All right. So at this point, I would go to spot 4. Can I use spot 4?
Yep.
Yes. So I would change the status code from 0 or -1 to 1. I would change the key from that old value that we didn't care about, because it's deleted data, not because we don't care about Doug. And then I would effectively erase the old 0 object and put a new 1 in. I won't redraw that. You just know what will happen. And now we have Brandon in the hash table. Does that make sense? All right, let's go down our list of questions. Can this hash table grow easily? In other words, can we easily add items into buckets? Yeah, well, we did.
Well, yeah.
Well, we can.
Oh, how can it grow past capacity?
No.
Not past capacity. Did the linked list have a max capacity?
No.
You're really limited by just your memory size. Can you remove items easily? Can you zero it back out? Yes. Is it compact size?
Yes.
No.
Yes, if mostly full. What if it? Well, I'd say it's more than linked list, and here's why. I'll say better. Suppose you had a bunch of buckets but a little bit of data. In both the linked list and array-based hash table, you will have a whole bunch of empty array slots. Agreed? So you'll always have empty array slots either way. Let's suppose that they get mostly filled up. You have most of your buckets filled. Who's more compactly using the data? Arrays. You're not worrying about extra pointers floating about. So I will say that arrays are better in using compact size. Are they speedy? Yes. That's why we like arrays. I know it sounds funny. It's just one more criteria, but that's why arrays always win. You come up with all these crazy fun data structures, and someone just says, "Oh, does it beat an array?" Shut up. I like it. It's good looking. I like it. I don't know. Arrays win. They just always do. What if you do lots of repeated removal and insertions? What's going to happen? Well, let's say you insert 6 and then you remove 4 and then you insert 7 and you remove 5 and you're just constantly inserting and removing, inserting and removing, inserting and removing. You go through many, many rounds of this. What will happen?
The hash function is gonna become kind of useless,
Why?
because you could hash to the number that you're supposed to, but if you do the one right in front of it.
Nah, there's more to it than that.
One, there's
What will happen to the status array if I just do lots of inserts and lots of removes?
It's gonna become all one.
It'll all be ones and negative ones. If everything is ones and negative ones, and I try to look up Denise, who's not in there, what do I have to do?
Search through everyone.
I have to search through the entire hash table as if it's an array. And now, is it any better than an array in the first place?
It's probably silly.
No. So hash tables are, array-based hash tables are very bad for repeated removal and inserts, because all those status codes, you lose all the zeros. And the zeros are the only thing to tell you to stop. Does that make sense? The only way to fix this is if after a certain amount of inserts and removals, you re-index. You make a brand new hash table and you grab everything you've got and pop it into the new one. That'll get you have a whole fresh batch of zeros. Can the hash table grow? No. It's just as bad as the linked list. You'd have to make a new hash table and copy over. Does it clump when filling up? Yes. Did the linked list one clump when filling up? No, they don't clump with neighbors. They only clump on their own collisions. Does that make sense? All right. Any questions on the array-based hash table approach?
So, question, if you, let's say that we were writing an array and we were going to be removing and adding items all the time.
Yes.
Would a linked list be better than an array?
It's two approaches. One is use linked lists, because linked lists do a much better job of removing and adding. The other approach is to just say, have some kind of a counter variable that triggers. It says, hey, if the count equals the number of buckets, re-index the whole thing. And you might say, well, isn't that expensive? And I'd say arrays are fast. You'd have to time it to know. At that point, you're smart, you're a CS student. Be smart and come up with your answer. Other questions? All right. Let's show you associative arrays in use. Now, this is not necessarily a hash table, and behind the scenes it's actually using a tree, what I'm going to show you, but this will show you or demonstrates a key value pair code in action. Behind the scenes, this could be hash tables. For our homework assignments, we will make this code work with our own hash table underneath the hood. But they're really fun. I'm going to include the tool called map. And I am going to do int main, and I'm going to create the same thing we did, a map. And this one is asking for the key data type and the value data type. It's a double template. Up till now, all your templates have been type name T. What if you had a type name T and also a type name U? Here they call it type name KTY and a TY. And they also have a third one if we ever need it, but I won't get to it yet. So let's do we'll do, again, names and money in your pocket. So the names are strings. So I gotta include string. And the money is just ints. We won't have negative money, no IOUs in your wallet. So it'll be a map of strings and ints, and I will call it students. I also need to have my cn.get, which means I need iostream and cn.
Should that be that order?
Doesn't matter.
Okay.
So I'm going to say students, good old IntelliSense. Let's say if we have an insert. We do. And does it give me the awesome new, does it allow the move? We'll try. Yeah, I think it did. I saw it. I'm going to say Doug we're going to have a 0 for you. Did it take it? Did it take it? Oh, I thought it would take it. What am I missing on this? Golden State's winning. Do I have to insert the old ugly pair way? I thought there was a way to make this work. The syntax gets really ugly the old way. I swear the new way worked, but I guess it didn't. What am I missing? Do we have C++11 code here? Oh, I'm missing something. I'll have to find it next time. We'll do it the ugly way. The way it works is they want you to insert full pair objects. So you actually have to create a pair of, and I actually have to specify the data types every time, don't I? That's even worse. Pair of string and int, Doug and 0. There we go. That kind of, a lot of you are not liking it already. We'll do a few others. Who do we have? Go across the back again. Carson. You had how much? 5? Let's keep going. Daniel was 0.
That's what he hashed to.
Oh, that's right. Daniel had 4. And keep going. Joshua 20. And keep going. One more. Dylan. You had 50. We had a comment here. Now the idea behind it is, yeah, this looks a bit ugly to set it up. See out. Dylan has this much money. I gotta make a, using std see out. Dylan has this much money. Students, Dylan. Using std and l. Yep. And this is the big powerful line of code I wanted to get to. It's weird to see a string inside of array subscripts. You're used to seeing numbers there, 0, 1, 2, 3, or 5. You'd want to think of Dylan as being at index 4 because we did 0, 1, 2, 3, 4. Maybe you want to know where the index is internally. You don't have to worry about any of that. You supply the associative array a key, and it goes and hunts down the value for you and returns the value. Does that make sense so far? Could I also say, how much money does Daniel have? Daniel has this much money. Yes. Let's try it, make sure I'm not lying to you. Oh, I did my return 0 there.
Yep.
My return 0 should be there. Dylan has this much money, 50. Daniel has this much money, 4. These are containers. Do containers support iterators? Yes. Can we write a fun for each loop on this? Yep, I think. Oh, it's going to be a for auto key value pair in students. The problem is my collection is a collection of these pair objects. That's the way they set it up. So it's returning a pair object. It's not returning a name. It's not returning a value. It's returning the name and the value. That's why I called it KV for key value. So I think I can say cout for key value dot first First is the first data member. The money is k value dot second. Oh, this is so cool. This is the big payoff. This is why we're doing all this work, so we can write very clean code. Any part of this for loop that's confusing you, please ask.
That syntax.
What syntax?
The auto KV students that I don't.
All right, do you remember that we did this syntax in our homework assignment? So, does students have a begin and end iterator? Or does it have a method for begin and end? Does a map have a begin and end on it?
I think so.
It has to make this work. Is KV an iterator? Or how do I say it? Does it support the iterators that begin and end return? Do they support operator star, operator not equals, and operator plus plus? Yes. So it has those 5 things that we talked about that you're doing in your assignment right now. This container also supports those 5 things. Because of it, if you wanted to see the old way, it would, oh my goodness, it would be for every map of string of int const iterator iter is equal to, I'll call it, yeah, iter is equal to students.begin. Does iter not equal to students.end plus plus iter. All right, and then I would say for key iter, or what's it returning here? Yeah, iter first, iter second. There we go. Now those loops are equivalent. Which one do you like better?
Definitely the second.
Because it gets the job done. It's basically saying for every key value pair in my students collection. Right? Is that helping? You're still not buying it all though. Tell me the other part you're staring at that you don't like.
It's, I don't know, it'd probably take a lot longer.
No, tell me, because other students are in the same boat as you.
I guess when I look at, so I understand that the second one has to have those 5 elements.
Yes.
And so, but I just am not quite grasping how 3 strings constitute all 5 of those. So your auto, your KV, and your students. I just don't get how all of those just form those 5 separate.
Oh, how those all come together?
Yes.
Well, what's happening is the compiler says, all right, you're trying to use the range-based for syntax. This is new syntax to C++11. It's awesome syntax. In order to pull it off, the compiler first checks the container and says, container, do you have at least a begin and end? And it will check the container, the map class, and look for a begin and end method. And the compiler will say, hey, I found the begin and end. Check, check. 2 of the 5 checks are done. Okay, what's the return type of the begin and end? Well, it says they're an iterator. Okay. Does that class, does that iterator support operator star, not equals, and plus plus? And it will look for them. And it will find all 3. Check, check, check. Compiler says all 5 checks have been satisfied. Therefore, the compiler will say the user wanted clean code, but I will expand it out this way because I can always turn this into that.
Okay. So the students is the container and the KV is the iterator object?
It's not the iterator object. The iterator object's actually hidden from you here. Okay. It's actually the dereferenced iterator. It's actually if you say go to iterator, go to my data. That's what KV is.
Okay.
Does that help?
Yeah, that helps.
Anybody else? Let's see what happens if I run this. Please compile, please come. Yes. Here's our first time around. Carson, Daniel, Doug, Dylan, Joshua. Carson, Daniel, Doug, Dylan, Joshua. Are those the same order that we put them in? Do hash tables really have an order? Do associative arrays really have an order? No, order doesn't really make sense here. It just, they go, you hash the key, and wherever it takes, well, the way we think of it as a hash table, we hash the key, and wherever it sends us is where we put it. Do we really have an order after we hash the key? No.
It's like it's sorting it alphabetically.
They are not using a hash table. Map uses a tree. And that tree is a binary sorted tree, sorting the keys alphabetically. We haven't got to trees yet, but they're pretty straightforward. But they do the same thing. They take the key, they look it up, and theirs do show up in order. But our hash tables will not.
Will it always start at the same position in the search?
What do you mean?
Wherever that position is, wherever that hash value lands, it'll always start in that same spot?
Yes, like if I were to say, Doug, let's hash your name hashed to 4. Your name always hashes to 4, so we will always go to spot 4. So it's deterministic that way. Does that answer your question?
I think so.
Yeah, you sure?
No, I'm not sure about any of this, but I think so.
Okay. Well, it didn't sound like I gave you a good answer. The biggest thing is that we don't have to worry about looking over all of it. We just say, hey, Doug, you hashed to 4. Bam, I go to spot 4, and I can start looking for you down at starting at spot 4. And you always hash to a 4, the way we set it up. It's not some random number generator. It's a hash table. Could we have a hash table of hash tables?
Yes.
Is that a good idea?
Yes.
Oh, yes. Can you do a hash table of hash table of hash tables? Sure. Is that a good idea? Yes. Can you go many levels deep? Is it a good idea?
Turtles all the
Yes. That's extremely powerful. It's a lot of fun. And some languages are just built on this idea of just saying, look, hashes, they're almost fundamental data types of other languages. If you ever program in Perl, it's one of the 3 fundamental data types of Perl. So next time, I want to get you I really want to do the linked list based hash table assignment, not the array based hash table assignment. The array one's too easy and I need to give you a challenge. I also need to talk to you about L values and R values and something called STD move. How do we move constructors, move placements? How do we, the goal is, how do we make sure that we're not making copies of objects anymore? In C++, it's very easy to say, hey, look, you're returning by value or you're passing in by value. At some point, copies are made, and copies can be expensive. So I will show you how you can start dealing with moving stuff. Or it's not a real move, it's a fake move, but it means we don't have to make copies. Other questions for me? All right, we forgot to get you a participation code. Let's find one.
71, 79?
Hold on. We could do, no, I need more numbers than that.
Oh,
We'll just go straight off this.
470.
All right, participation code is 470543. Again, 470543. If you also put that in online, it will also give you some of the answers to your current homework